All right, this is physics, and we are in the middle of Module 5, and we've just completed a section on Newton's second law, which is force equals mass times acceleration. And at the bottom of page 148, where we start our reading today, it says, one important application of Newton's second law involves distinguishing mass from weight. Okay, so mass, it says, is a measure of how much matter is in an object. Weight is a measure of how hard gravity is pulling on an object. Okay, so we want to make sure that we have a proper distinction between mass and weight. Look at the last paragraph on page 148. Now, obviously, I'm not reading everything, so you make sure that you read carefully. Okay. Another important difference between mass and weight is that mass is a scalar quantity, while weight is a vector quantity, right? Because weight is a measure of a force. It's the force with which gravity pulls on an object. And so if gravity changes, weight changes, but mass doesn't change, right? So as you visit the different planets in our solar system, your weight on each planet would vary because the gravity on each planet or other celestial body, say the moon, the gravity would change, right? But your mass presumably would stay the same. Now, obviously we have ways of changing our mass, I guess. But the point is, as long as we live on Earth, if our weight changes, assuming that force of gravity doesn't change, something else must have changed in order to increase or decrease our weight, right? And that would be mass. So at the top of page 149, we see equation 5.2, and this would be something you want to put on your 4-inch by 6-inch reference card. Equation 5.2, weight equals mass times gravity, or the acceleration due to gravity. By the way, just a reminder to you, in your textbook, in the inside front cover, you have a list of physical quantities, and then on the facing page you have some other information that can be helpful to you. On the inside of the back cover, you have conversion relationships. Okay, so converting from one unit of measure to another unit of measure. And then on the facing page, you have some other information which can be of value to you. I don't know. See, I don't think he has in here. I don't think he has. Wait, let me take that back. In Appendix A, I thought he did. Appendix A, which begins on page 557. Maybe I've mentioned this before, but there you have a list of all the different formulae that we will use throughout this course. All right, so that can be another reference for you, as well as just keeping information on your 4-inch by 6-inch card. Okay, so just resources available to you in your textbook. Okay. Okay, so we got this formula then: weight equals mass times acceleration of gravity. So let's see. In the paragraph following the paragraph that includes equation 5.2, our author takes up some units of measure that we need to be aware of. Okay, when you weigh yourself in the metric system, the measurement is done in newtons. Okay, Newton is the metric unit for weight. Right? What about the weight unit you're most familiar with, the pound? Well, It's the English unit for force. Right? You may have heard of the description of pounds per square inch or something of that effect, right? Remember, you just learned that any displacement unit times any mass unit divided by any time unit squared is a valid unit for force. The standard English unit for mass is the slug. All right, so this is an English unit, the slug. I suppose I should have, let me get Newton off the board here because we're talking English units now. So the slug is the standard English unit for mass. The standard English unit for displacement is obviously the foot. So the standard English unit for force is slug times displacement, right? Divided by time squared, seconds squared. And that is the pound. Okay? So, in the English system, when you are talking mass, you're talking slugs. When you're talking force, you're talking pounds. So let me read paragraph on page 149, which begins, this is one of the first places, it's the paragraph just above the bold text near the bottom of page 149. Let's read through that. This is one of the first places students get confused when dealing with problems that use mass or weight. When physicists refer to an object, they will rarely say things like an object whose mass is 15 kilograms. Instead, they will generally say a 15-kilogram object. Physicists expect you to realize that since the unit kilograms was used, the measure must be the object's mass. So when we're talking metric, I'll do metric in a different color here. Mass is kilograms. Or grams, you could say. The base unit grams. In the same way, physicists will not often use the term weight when giving you the weight of an object. Rather, they will simply give you the number with a weight unit, pounds or newtons, and expect you to realize that this means weight. Okay, so in the metric, weight is newtons, and in the English, weight is pounds. Okay, so what has our author said? Rarely are you going to read the mass of an object is or the weight of an object is. It's going to be a 15-pound object, and you're going to know that that is the weight of the object. What does that mean? It's the mass times the gravity of the object. Or they're going to say, a 5-slug object. You're going to know that that's the mass of the object. Finishing with that paragraph we were reading, thus physicists interchange mass and weight rather freely, expecting you to tell which is which by what unit is used. You must therefore become very comfortable, recognize the difference between mass and weight by recognizing the units. Right, now, what we have in bold here, this is something that you'd want to be writing down. See it, say it, and write it. Use all three of those to help yourself remember it. When a measurement is referred to in slugs, grams, or any prefix unit based on grams, that would be milligrams, kilograms, etc., the mass of the object is being reported. When a measurement is given in newtons, dynes, or pounds, the weight of the object is being reported. Okay? Now, if you go back to the inside cover, the back cover inside, you will see under force, you'll see the units Newton, dynes, and the lbs for pounds. Under mass, you will see slug, kilograms, or the base unit gram, right? And so that'll help you. That can help you remember, right? Look back. You're dealing with a particular problem, and they give you a unit. If you're not sure, look back here at the back cover, and if the unit falls under the mass category, then you've been given a mass. If it falls under the force category, you've been given a weight. Because remember, weight is the force of gravity on the mass of an object, right? Okay. So on the next page, we have an example problem, right? Page 150. A man steps on a scale and determines that he weighs 151 pounds, equivalent to 672 newtons. Determine the man's mass in both kilograms and slugs, right? So here, we would know, okay, so let's deal with the newtons, right? We're told 672 newtons, that would be the weight, because weight is a force, or what do we say? Weight is a vector quantity. It includes a force and a direction, right? And what does that equal? It equals mass times gravity, right? But we know gravity. In this case, we know gravity in the metric, so that would be 9.8 meters per second squared, right? So think about what we figured out here. We figured out that newtons was metric, and it referred to the weight. And so that led us to put newtons in the place of weight in our basic equation here. We're trying to find the mass, so we have an m. The acceleration due to gravity we write in terms of metric, 9.8 meters per second squared. Okay, so pounds, you probably get the idea. Pounds is the weight, so this is 151 pounds. Well, what is that going to equal? Well, it's going to equal the mass, which we don't know, we're trying to find, times the gravity, 32 feet per second squared. Okay. Now, when we solve this for mass, okay, we expect the on the metric side, we expect the mass to come out in kilograms. One thing to remember is those newtons, and if you are ever uncertain about this, either have it written on your reference card, or you're going to find it in your text. Where was that given to us in our text? Oh, wherever newtons were in, there it is. It's kind of the lower part of page 146. Oh, actually, it's in the bold on page 146. Remember that newtons are kilograms times meters over seconds squared. Okay, that's the complicated unit that we call the Newton, right? Here's an important thing to keep in mind. When you're solving these, if you're on the metric side and you're solving for mass, you're going to expect your answer to be in some form of grams, right? The base unit grams and then some prefix to it, kilograms typically. Okay. In fact, given newtons, you will specifically be working with kilograms, right? Now you may want to convert it at the end to simply grams, depending on how the number shows up. Over here with the English units, right, you're going to end up with slugs. Okay, so remember that pounds is the complicated unit, slug times foot. Remember, it's mass times displacement divided by time squared, second squared. Okay. All right. And so the next thing to be careful about, and I noticed this on maybe one or two problems in the last few assignments. Be careful about your algebra at this point, okay? Notice that in both cases, to solve, I need to divide the weight by the acceleration due to gravity, okay? Sometimes it can be helpful, rather than getting the numbers in and getting lost in all the numbers, right? That weight equals mass times gravity. I can rewrite that as mass equals weight divided by acceleration of gravity. Right? And really, those two forms, weight equals mass times acceleration due to gravity, and mass equals weight divided by gravity, are really the two forms that I would need this. I would put this on my 4-inch by 6-inch reference card, just so I have it. Am I trying to find weight? What do? Am I trying to find mass? I know exactly what to do. Take the weight and divide it by acceleration due to gravity. Okay. I mean, you could do the third option there, that gravity equals weight divided by mass, but gravity is a constant. Now, I suppose you may end up with a problem where you're on some unknown planet, and for some reason you know the weight and the mass, and you want to find out what's the acceleration due to gravity of a planet. So, I mean, I guess there could be a scenario where they would give you that problem to do. Okay. As far as the math goes, it's pretty straightforward. I mean, it's a very simple equation, and so it's very simply solved. Just make sure that you're using the 9.8 meters per second squared for gravity when it's in the metric, and you're using the 32 feet per second squared for acceleration due to gravity if you're in the English. Okay? Now, on the top of page 151, he talks about what he thinks is something rather important, and he says this: it turns out that when we measure the mass of an object, we are often, in fact, measuring its weight and then doing a calculation like the one we just did in order to convert that weight into a mass. Okay. And so he points out an example from a chemistry class where you put the reagents, the things that are involved in the experiment that you're doing, on a scale and reading the mass in grams. It turns out, however, that a scale does not measure the mass of an object. And so he talks about the scale and that it's composed of a spring or a flexible needle sensitive to the force that it exerts. When an object sits on a scale, gravity tries to pull the object to the center of the earth, but the scale stops that from happening because the spring or needle in the scale pushes back with a force equal to that of gravity. Since gravity pulls the object down and the spring or needle pushes the object up with an equal force, the forces cancel. The scale, however, can read the force exerted by the spring or needle. Thus, since the scale reads force, it measures weight. How do we read the mass in grams then? Well, the makers of the scale simply take the weight and divide by the acceleration due to gravity, turning a weight scale into a mass scale, right? So the point there is that the scale does the conversion for us, right? By the inclusion of a spring that counters the force of gravity, and then a scale on a measuring scale on the scale that you're using that gives what would be the mass. Okay. Well, look at what our next example is. An object weighs 3.42 times 10 to the third pounds on Earth. How many pounds will it weigh on the moon? The acceleration due to gravity on the moon is 5.3 feet per second squared. All right, so it's similar to what I was saying. that there could be a scenario where you need to find the acceleration due to gravity on another celestial body, but in this case, what do we need to do to solve this 5.3 before we read on, this example 5.3, before we read on in the answer? Let's think about what we need to do, okay? Well, if we know the weight of an object on Earth, right, and we want to find out the weight of the object on the moon, we remember that weight equals mass times acceleration due to gravity, right? Well, we can take the weight on Earth and find the mass. Once we have the mass, we can take the known mass of the object and multiply it to the acceleration due to gravity on, in this case, the moon, and we'll get the weight on the moon, right? That makes sense? We know the weight of the object on Earth. We can find its mass. Why do we want to find its mass? Because we want to multiply that to the acceleration due to gravity on the moon to find its weight on the moon. Okay, so look at the top of page 152. There you see our Earth weight, and we're saying that equals the mass times acceleration due to gravity on the Earth. Notice it's 32 feet per second squared because we've been given the weight in pounds. So then we solve this. Notice in the second line where he's got m, or mass, equals, the pounds unit has been converted to its complicated form, slug times feet over seconds squared. And he simply does that so you can see what's happening with the units and why it is that we end up with an answer of slugs. But that top half of the box on page 152 shows us how we found the slugs, the mass of this object that weighs 3.42 times 10 to the third pounds. Okay? 1.1 times 10 to the 2, or 110. That's the mass of the object, 110 slugs. It doesn't matter where that object travels in the universe, its mass is 110 slugs, assuming that it doesn't for some reason gain mass or lose mass. Right? Okay, now what is it the problem is asking for? What's the weight of this object on the moon? Well, using the same equation, we can find the weight. This is the bottom part of that purplish box on page 152. We can find the weight because we know the mass. So let's multiply it to the acceleration due to gravity of the celestial body upon which it sits, and that's the moon now. And so we do the multiplication. We end up with a slug times foot over second squared, or a mass unit, slug, times displacement, feet, over time squared, second squared. What is that called? That's called a force. In English, we use pounds for force. So it's 5.8 times 10 to the second. that'd be 580 pounds on the moon, right? Move the decimal point 2 places to the right. So on Earth, moving the decimal point 3 places to the right, 1, 2, 3, that'd be 3,420 pounds. That seems pretty heavy, but it's only 580 pounds on the moon. Okay? I think that that's not uncomplicated. Your responsibility then is to read these pages, starting on page 148, mass and weight, and read to the on your own questions on page 152, right? So you're reading pages 148 to 152, and then you're going to do Oyo's 5556. Okay, that's your assignment for today.